to close the window so we don't have too much noise from the work outside. At least try to. Okay. So, if you remember, last time we found another way to solve the two-level system, which was the Bloch optical Bloch equations. And I'm not going to derive again what we did last time. I'll just remind you of the consequences. I mean, everything started from saying, look, there is this density operator, which we called sigma. Well, this density operator, this density matrix, tells us the measurable quantities of the ensemble of the experiment. So what is the ensemble of the experiment? Well, it depends. Maybe you're doing many experiments on a single atom. Maybe you're doing one experiment on an ensemble of many atoms. Maybe you're doing both. But in any case, there's always an ensemble of results. And out of this, you get all kinds of statistics. And there are measurable quantities that you could measure. And what are they regarding the state? Well, of course, you cannot say, I mean, you cannot measure these C1 and C2. But you can define this. As we know, this is a matrix. And sigma as a matrix is nothing but C1 absolute value squared. On the diagonal, it has the populations. And on the off diagonal, it has the coherences. And clearly, because the total population is 1, and because the coherences are complex conjugate of one another, there's only 2 parameters in the game. 2 actual parameters. Now, and we can write the dynamical behavior of this, because as the state changes, so does the density matrix. And it's very simple to write. And we did that last time. What we're going to do now is to actually, last time we discussed this. Now, basically, it looks like a bad idea to solve the two-level system that way, because it just seems complicated for no reason. But as I showed you, we can reach from this density matrix formalism to a convenient, very visual model of a spin vector, a fictitious, a pseudo spin vector, that is has very simple dynamics in a field, which is just like a magnetic field. So that's the reason why to go there. And today we're going to see the other reason to go there, because today we're going to introduce decay. But the decay is going to be added by hand, because classical dynamics or classical field doesn't incorporate any decay. Or at least the Hamiltonians that we have don't show any source for decay. So there is, this one is not great. Let's use another, hoping it will be better. Yeah, much better. Well, maybe I think that if we do this, there's probably need to be I here as well, but and this, well, this is saying something like maybe this is the derivative due to the dynamics, and this would be the derivative due to how do you call expressed dependence on time, if there is some תלות מפורשת בזמן. And now there is, I said it once, I'll say it again, there is no reason to think about this term. It doesn't exist anywhere. We're going to just invent it and put it there.
Is it
yes?
directly measurable?
What?
Is that added expression directly measurable?
Actually, yes. So, yeah, I mean that that's the only reason we add it by hand, because we need it to explain the measurements, because otherwise things don't add up. Now, so, but let me remind you that, okay, we can write, of course, put here this sigma and the Hamiltonian. Another quick reminder, and that is that usually we work in the rotating base approximation, where we write, well, C1 ground doesn't change, but C2, we add to it a rotating term, omega laser T, and not ground. Excited? And when we do this, then the Hamiltonian, our Hamiltonian under this within the rotating wave approximation, which is a very good approximation, because within the optical frequencies, the counter-rotating terms, which we throw away, are rotating so fast that they really average to nothing. And then the Hamiltonian is simple. It's just 0 delta omega star. And with this and this definition of we can write the equations. But as I showed you last time, we can redefine vector we can define a fictitious state vector, which is the vector we called it raw, which is u, v, and w. And those are just real part of C1, C2 star, imaginary part of C1, C2 star, and W is the population difference, C2 minus C1. Now, I think that we had a half here. So, well, divided by 2. What? Yeah, up to a constant, everything's fine. Now, this, what's nice about this vector is that if we, first of all, this vector includes the 3 true important parameters of the density matrix. Because the sum of populations is not important. The difference of population tells us the population inversion, or it tells us everything about the population. And the real and imaginary part of the coherence, they tell us everything about the off-diagonal elements of the density matrix. And the other thing is that it makes a really nice dynamic equation, which is to say that, okay, before that, we define this vector, which is the state vector, and we define another vector, which is the field vector. And it looks like this. And then the dynamics becomes under these two definitions, so which is defined like that. We have a simple dynamic equation which says rho dot equals omega cross rho, and that's a nice convenient dynamics because this is simple mutation, just like a spin rotates around the magnetic field in a magnetic field, or just like סביבון. Yeah, just like a top rotates around the gravitational field, does nutation. The same thing happens here, and we have this fictitious spin rotating around this fictitious magnetic field. And actually, this entire dynamics was discovered or was written by Bloch for real spins in a real magnetic field in the context of NMR. And that's why those are the Bloch equations. And then I think that Feynman was the one. Many things belong to Feynman, who just took them over to the optical domain and wrote said any two-level system is effectively a spin, and any two-level Hamiltonian can be effectively discussed as generating spin dynamics. So the dynamics of any two-level system, it doesn't even matter if it is, it could be an atom in an optical field or whatever it would be, that's all that it does. So this is a very general solution. And actually, it comes from what we did last time was to look at several simple possible dynamics of this. And that is to say, OK, here is my UVW fictitious space. So that's, I don't know, U. Maybe better make that one U. VW. Why? Because the field, because it's more convenient to make the nutation go around in the plane of the board. So, for example, if I have a field which just has a Rabi rate, a strong Rabi rate, and no detuning. So this was an on resonance Rabi oscillation. And then we could say, OK, if it's on resonance, then there's no detuning. So this is where the field is. And suppose that we start with the atoms. I don't know where we start with the atoms. But let's assume now that we start with all the atoms in the ground state. If all the atoms are in the ground state, then C2 is 0, C1 is 1. So what we have is minus half. So this is where we start. This is rho at time 0. And then all that happens is that it nutates around the U axis at a rate that is dictated by the strength of omega, by the Rabi rate. So all that happens is that it does this. of course, it can continue. And now we can define pulses. Up to here, it's a pi pulse. Up to here, it's a pi over 2 pulse. By the way, all the way to here, it's 3 pi over 2. And you can see that if you give it 2 pi, then you go all the way back to 0.
Can I ask a question about it?
Yes, I guess.
I mean, what is the meaning of sending a pi pulse? I mean, it's the time of the pulse?
Yeah, it's the time that I have the field on. Think of it as the following. You don't even, what's even more convenient is to think about that. The laser is always on. You'll see in a moment why. There's a shutter that blocks it from the atom and then lets them in. So it lets the light into the atoms for a time that matches this. So when we talk about the phase of the pulse, then we should say that this is, if I say that a pi pulse, meaning that pi is what? Is omega, in this case, omega 0 times tau, and omega is the dipole times the field divided by h bar. And that should be pi. And actually the field, we should think here about the amplitude of the field. Now this is not the intensity, it's the amplitude of the field. So, and then, okay. And then we started to think about all kinds of possibilities. One is, okay. And then there's okay, so that was on resonance. Let me draw also the off resonance case. The off resonance case is rather simple. It will be harder to draw though. But I'll mention it here. If we are off resonance, oops, never mind. Oops. If we're off resonance, then that means that omega is not pointing exactly in the u direction, but it actually is pointing a little bit up or down. So I don't know, maybe let's do it like this. And this is here. And this is delta. Now that means that the nutation still happens, but it nutates around, it nutates in in a plane which is not the VW plane. So we are moving on a sphere of radius 1 or half. The entire dynamics is happening on a sphere. We could move. In one case, we were rotating this way around. Maybe now we'll be rotating. I'll try to do it like this. So instead of rotating in this plane, it's going to be a little bit like, I don't know, like this. Because because we're rotating around. So the blue case is the detuned Rabi oscillation. And in this case, I'm out of colors, but well, it's hard to draw. You are nutating around a vector that is not in the VW plane. And then there's another thing that we should say, and that is note that the relation between the detuning and the Rabi rate is important. For a given detuning, you can have a vector that is almost perfectly aligned if you have a very strong field. A very strong field doesn't care about the tuning. A very strong field becomes nearly perfect. This is, in other ways, is what we call power broadening. I'll explain why. If you have sufficient power to drive the atoms, it doesn't matter if you're detuned or not. I mean, you'll drive them, you can almost complete Rabi oscillations. They'll go around rather fast. So the atoms, you know, the atoms, they won't stay up enough time to understand that they're operating against a detuned laser. They'll be running around, whoop, vroom, vroom. They'll do many rotations very quickly. Overall, I mean, the population is going up and down and up and down and up and down. And the fact that the laser is detuned is almost not, you can't feel it. Why? Because you complete a revolution in a very short time. And you don't notice that there is an energy mismatch. You know that delta E, delta energy, delta T, that is limited by Heisenberg uncertainty. But if the time that you take to make a complete circle and come back and forget whatever happened is very short, you can suffer a detuned case, meaning you were transitioning by the wrong frequency, but you don't know it because you didn't spend enough time to feel it. So this is just, you know, this is just Fourier uncertainty. Or so if the field is strong enough, detuning is not so critical. But if the field is weak and the Rabi rate is slow, then any detuning becomes noticeable. So the question is, what is the detuning? It doesn't matter what it is absolutely as an absolute number. What matters is what is the detuning relative to the Rabi rate, or the other way around. So, and you can see that if we do a Rabi pulse slowly, that meaning that we employ on purpose a low intensity field. So this transition goes around slow. Why is that good? Because you actually want to measure the detuning. You want the laser to hit exactly the atomic transition. Why? Because you want to make a clock. You want to make an atomic clock. The laser actually doesn't have to be a laser. We call it a laser because we're talking about quantum optics. But of course, it can be in radio. It doesn't matter what is this separation. I didn't tell you what the frequency is. And this was something that people understood long ago, that if they want to measure the frequency of the atomic transition very precisely, they want to drive the transition with low intensity light, as low as possible. Okay, on one hand, you could, from what we did here, it seems that if you do it with the lowest intensity, turn on like just very faintly the laser, and the atoms will go very, very slowly like this. It will take them an hour until they go up. And then, and then you'll be precise to within what? Tell me how long it took you. If it took a second, then you'll be precise up to a hertz. Because the uncertainty of the frequency is just 1 over the time. The problem with this, this is true if this was the entire picture, but of course if you take it, if you want to do it in a second, then the atoms will never go up because they'll decay before that. Because then decay plays in, and we'll discuss this now. So they understood very well that, and the limit is then dictated by the decay or decoherence mechanism that exists, meaning what's the slowest that you can run this dynamics without interference from other things. Usually that is the lifetime of the excited state. So if you want to make a clock and to measure this atomic transition very precisely, then what you would like to do is to have a Rabi pulse that is sufficiently weak such that the transition is on the order of the excited state lifetime, because that's the longest you can make it. Tell me how long does this excited state live? And that's about as long as you can run it. And that would be the most precise measurement you can do. The problem was, this would be the Rabi clock. The problem was that everybody understood it and nobody could make it. Why? Because they couldn't, well, when we're talking about 60s, 50s and 60s of the previous century, which means when I was a kid, and well, no, I wasn't a kid then, but not, you know, my parents were kids at the time. And then the problem was that the atoms, they couldn't hold the atoms. Today, we can cool atoms and trap them, and they sit, and you can do exactly that. The atoms are not going anywhere. They're cold. They don't have special velocity. They have almost no zero Doppler shift. So they just sit quietly and wait for you to interact with them. And then you can do exactly what we just said. The problem was that at the time they didn't have that. They had a beam of hot atoms, and they didn't have any way to cool them. So they had atoms at room temperature or higher than this, coming out of an oven and flying at a thermal speed until they hit something. So the first thing would be, okay, let's make sure that they don't hit anything. So they make a long pipe. Okay, so there's an oven sitting here. You see here. This is the oven. And from here there's a hole, and it sprays hot atoms, and they're flying through the pipe that is sitting here. As you can see, I'm holding it. And, well, somewhere there's a wall, so we cannot let them fly in too far. And then, okay, so the atoms are flying at thermal velocity through this vacuum pipe. Now we want to interact with them. Okay, so if I want to interact with them, and I want to interact with them for a long time, I have to do it over also a long distance. And now there's a technical problem. Because I cannot make a field, you know, a laser beam, or at the time it was a radio beam, but still it's the same problem, that is this big and perfectly coherent. And and then that means that the time of interaction with the pi pulse was limited not by the excited state lifetime, but by the technical limit of making a large radio beam. This was done in some radio cavities that were built around that were built around the atomic beam, and there was no way to make them bigger because of technical limits. So that's why the precision of Rabi clocks at the time was limited by the time of flight of the atoms through the cavity. Actually, I'm telling you, look, we will turn on the light and turn it off. I'll have a shutter, I'll turn on and off. They weren't doing anything like this. They were continuously transmitting into the atoms. The atoms were just flying through. So the shutter was the atom coming in and coming out. And then came Ramsey and said, we can get the precision of the long time without the need to build a very long, physically long laser beam or a laser field by splitting the transition into two parts. Meaning, so now I'm reminding you about what Ramsey did. So Ramsey said, okay, you can do only short pulses? Fine. Great. Let the pulses be short. Oh, U, V, W. We start from here, but let's do it in 2 steps. So this is this rho 0, and we take it with a pi over 2 pulse here. And then we wait. So this was, yeah. We had a pi over 2. So we're talking now about Ramsey interference. They're called Ramsey fringes, or Ramsey interference, or Ramsey configuration. It doesn't matter, but the point is that there are 2 pulses. There's a pi over 2 pulse. You wait for a time t, and then another pi over 2 pulse. And those are short. Actually, they can be very short. Now, what happens? Well, of course, what happens is that first you go into, so this short pi over 2 pulse brings you to the UV plane. And now, but now you wait. And now it depends on the detuning, because your laser, as we said, is detuned. The atoms are flying and they are evolving at the atomic coherence, at the atomic. I mean, the atoms are now in the dark. What do they do when they are in the dark? Well, we know what the 2-level atoms does when it is in the dark. The excited state acquires a phase relative to the ground state. At which rate? At the atomic rate. So when the atoms are flying from one part of the beam to the other part of the beam, somebody remembered late. So when the atoms are flying from one side, from one part, or from one cavity, one radio cavity to the other, they are evolving, they're acquiring phase at the atomic rate. On the other hand, the laser is still rotating. As I told you, it is continuously on. But it is acquiring phase not at the atomic rate, but at the laser rate. If those 2 rates are the same, then nothing happens. If those 2 rates are the same, then the first pi over 2 takes you here, and then everything rotates at the same rate, both the atoms and the laser, and then they just end up here. So this is, if it is on resonance, then everything's perfect, except the marker, which is not perfect. Maybe we should try throw this one away and take another.
Avi?
Yes?
We are still not considering decay?
Not yet. We understand something that this probably, you know, that these tricks that we are playing cannot work beyond the decay time, but we haven't added it yet.
Okay, thank you.
So, and then, but of course, if it is off resonance, then once it is here, it will start rotating in the UV plane at the rate delta. And then what will happen is, of course, now it depends on the question of what is delta times t, because delta times t defines the phase that is acquired by the atoms relative to the laser. So then we have this delta phi, the phase difference, is delta times t, the time that is waiting between the 2 pulses. And of course, if this detuning, or delta times t, is, let's say, pi, then we'll move from here to here. And instead of going up, we'll be going down. This is the case of this one. The first one is the case of, this is delta equals 0. And this is the case of delta equals pi over t. And you can see that now everything is proportional to 1 over t. Everything, the scale for the detuning is no longer the time of the pulses, but rather the time between pulses. How long can we make this time? As long as the atoms remember. So we're going to somehow, again, so how far can we make those two cavities? Can we make them a kilometer apart? Probably not, because the atoms have a limited memory. And the question of what is this memory, what is this limit, this is the subject of our discussion today. So you can actually calculate so if I talk about what is then, say, what is W final as a function of the detuning, then it looks basically like this. At 0 detuning, we go up to back to, I don't know, if this is, we said this is plus half. And then at this is pi over t. We go to a minus half, and then basically we go up and down, and eventually it decays because it decays on a time scale. Okay, I'll tell you in a moment. So this is what we have. That's how things look. So this width is of order 1 over t or pi over t. And this width is of order, tell me how long each pulse by itself is. So this width is of order, if we said pi, so let it be pi over t here, and pi over tau, where tau is the duration of each pulse, the short time. And actually, this picture is the Fourier transform of this temporal profile. Just as a double slit diffraction is the Fourier transform of the two slits in space. So this is a double slit experiment performed in time. Okay. And for understanding this, Ramsey got a Nobel Prize because he could gain an order of magnitude in precision without doing anything to the clocks, just putting another cavity. Okay. So this is nice. So now let's say a few things. Okay. There's one more thing that I want to say. So, okay, so before we add in decay, the dynamics is limited to the face of a sphere. I have a vector with the length 1. And this vector is moving on the Bloch sphere, on the face of the Bloch sphere. I can do pi over 2, and then maybe, I don't know, weight, and then another pi over 2, and I don't know where I'll end. So, I mean, and I can choose also the field that I'm rotating about. By the way, we are always saying, look, the field is always in the u direction. But actually, that depends on the phase of the field. There's nothing. The field is on the u direction if we assume that the field is real. I can assume that the field is imaginary, and then it will be in the v direction. So that basically, so let me describe one quick experiment for this. If you remember, we discussed photon locking. We actually discussed an adiabatic passage. Adiabatic passage means that we start from a field that is highly detuned. What does it mean, highly detuned? It means that the field is pointing either almost completely down or almost completely up, but it doesn't matter. Why? Because in any case, what will the atoms do? The atoms are also pointing down, so they are mutating around the field. But the field is almost down as well, so they're almost doing nothing. And then we slowly change the detuning. So if we change the detuning, we'll be doing this. Okay. And then if I continue, this is when the detuning is actually 0. I'll reach here. And the atoms will be rotating here in the xy plane. Now, if I continue to change the detuning, then eventually to the other sign, I'll eventually end up with all atoms up. But the point is that now I can drag them anywhere. For example, if I want to drag them here, all I need to do is change the phase of the field slowly. So I have a field that is with 0 detuning, but change its phase slowly, and you'll move the atoms. Around. So you can drag them anywhere around the Bloch sphere by doing this. Or, of course, another thing that you can think of is maybe doing a pi pulse. Sorry, a pi over 2 pulse. Now, in this case, the field is here, and the atoms are there. So, vroom, that's all that happened. And now, I can very quickly, no longer adiabatically, quickly rotate the phase of the field also to point in this direction. And then what happens? We lock them here. So this situation is a very common one. And I'll say another thing, and that is that those of you who have heard about the Poincare sphere for polarizations, it's exactly the same thing. And so the dynamics, this dynamics is very common. Why? Well, because polarization is also a two-state, a two-level situation. You have two polarization components that are orthogonal to one another, just like the ground and excited. And those two polarization components, they have, when you operate with them, with all kind of elements, then you're doing things that are very similar. For example, a pi over 2, what does it do? Sorry, a pi pulse, what does it do? Well, we just said it takes this and takes it up. But actually, that's wrong. Well, of course, this is correct for this case, but this is a spatial case. I could be, I don't know, the vector could be anywhere. If it is down, it will end up. If it is on this place, it will end up here. If it is here, it will end up there. So what does it do? Well, it does, so we understand this dynamics. And then what is the equivalent for a polarization element? The answer is a wave plate, half wave plate. So it's a half wave plate. What about a pi over 2? A pi over 2 pulse is like a quarter wave plate. Now, I'm not going to teach you about the Poincare sphere. You'll learn about it, or you may have learned about it already. I'm sorry, somewhere. But it's exactly the same dynamics. And then, when we think about the Poincare sphere, then מישהו רוצה להיכנס. Should we let him? We just did. So there is this Bloch sphere or Poincaré sphere. And then here we just said there's a north pole and the south pole for polarizations of light. This is the clockwise circular polarization. This is the counterclockwise circular polarization. And as you know, if you make, and then on the diagonal is all the linear polarizations. And by wave plates, and by manipulating wave plates, you can, by using wave plate, you can move around the Poincaré sphere. And as you just saw, what we were talking about here was exactly the same. So if you've learned about the Poincaré sphere, good. And if not, when you, okay. Those of you who've heard about the Poincaré sphere will now say, aha, then I understand much better what happens with the atoms. And those of you who haven't say, what? But then when you'll see the Poincaré sphere, you say, aha, I understand better what happens with polarizations. Okay. So that basically, that was a very long repetition of things that we did last time. Now I want to say something about decay. So, we want to discuss the optical Bloch equations, but now we add decay and decoherence. So this is our subject. Now, it's late. You're coming late. Huh? Okay. This is the quantum optics course. So if you're not planning of sitting in the quantum optics course, then you can leave. But if you do want to sit in the quantum optics course, so we want to discuss decay and decoherence. And as we said, there's going to be time scales. So now I'm going to write, I'm not going to use this compact form of the dynamical equation, but write it as it was, which was to write that W dot equals U dot equals and V dot equals, let's remind ourselves, oh, come on. I'm sorry. Okay. So this is what we had. Minus omega W. So those are the equations that we had. And now we're going to put in some decay. Now, as we said, this is phenomenological. We're adding by hand things that appear in the experiment and seem to disappear from the dynamics. And that is the fact that there is a limited time for this dynamics to occur. There are two things that happen, and those are not exactly the same. So I'm going to put in two time scales of decay, and I'll try to explain why and what their sources are. So we have the time scale of decay of population, and it has a standard universal name, T1. Okay? So we put here, we say, look, this W, it doesn't only do this, it also decays. How? Where does it decay to? Well, of course, it decays to minus half, because everything decays eventually to the ground state. So there is W plus half, divided by the time scale it takes for the population. If you have population in the excited state, eventually it decays by some unknown mechanism and ends up in the ground. So W, if you do nothing, it decays on a time scale of T1. So T1 is the population decay time. It's basically related to the lifetime of the excited state of the atomic ensemble. Why is it there? I don't know. But it is. And then there are also these guys decay. What do I mean? Suppose now that, as I told you, I'll take the atoms with a short pi/2 pulse into this UV plane and leave it there. My laser is perfectly on resonance. It is perfectly on resonance. I'm doing exactly this. Now, I do a pi/2 pulse and just wait. Now, if I wait for a short time, I'll do pi/2, wait a moment, pi/2, everything, I'll see all the atoms in the excited state. But if I wait, I'll see less and less atoms in the excited state. It appears as if this U component is decaying by itself. It just has this minus U over T2, and this time scale is different than that one. It's actually usually faster. And the same goes for this one. So here, minus V over the same T2. Well, of course, U and V, there's no difference between them. They're actually just the real and imaginary part of the same thing. So if the coherence decay, there's no real reason to assume that for some crazy, what would be the mechanism for which the imaginary part will decay at a different rate than the real part. But maybe there are cases where this could happen. For example, parametric excitations. But where they will not be discussed, they will not be discussed here. So now all we did was to add terms. Now let's say something about the source of these terms. This is simple. T1 in a sense is simple. We don't know why, but there is spontaneous emission, and spontaneous emission just changes the populations. Excited atoms don't stay like that, and they decay to the ground state. So the T1 is simple. This is just, T1 is just normally the excited lifetime of the atoms. By the way, it doesn't have to be only spontaneous. It could also be driven, for example, by collisions. I mean, if we have an ensemble that is very dense and contains energetic particles that can hit the atoms and cause a transition, then they will make the transition time shorter. So T1 is population decay time, and it is, we can say that, so, okay, so I want to discuss, but before I say that, we put in T2, so T2 is what we call the coherence time. It has to do with the question of, if I am in the UV plane, for how long do I know in which direction I'm standing? If this vector quickly decays to 0, then it loses memory and it doesn't remember its phase. It doesn't know where it is in the plane. And so this is the coherence time, and we'll discuss both of them. No. So we want to discuss decay and decoherence. What time is it? Oh, okay. We'll have it. Okay. Yes. Yeah. So we just met this. So we can say that this 1 over T1 is the population decay rate. And this can be due to spontaneous emission, but it can be also due to collisions. If you have a dense and hot ensemble of atoms, so whatever it is that causes the population to decay is included here. And as we said, so now, and 1 over T2 is the coherence decay time. Now let's understand what can cause this. Now, and this is, now of course, okay, and I'll say something in a moment. One thing that I have to say is that, first of all, T2 is always less than T1. Because if the population of the excited state doesn't live anymore, then of course also the coherence between the ground and the excited state does not live anymore. Because the coherence, if you remember, is this C1, C2 star. If C2 went down to 0, then it doesn't matter anymore what the coherence is. So of course, the coherence time cannot be longer than the population decay time. But in many cases, it is it's not just shorter, it is much shorter. Now, I'm not saying that it always is. For example, in the ideal case that you have a single atom sitting quietly in the ground state, in the ground of a trap, not moving, temperature 0, and you're shining light on it, then you'll be in a situation where T1 and T2 are basically limited by spontaneous emission, by the spontaneous emission of the atom, and both of them become the spontaneous lifetime of the atom. But when you have either atoms that are hot and are moving, for example, that they have a Doppler shift, or if you have atoms that collide, then things start to change. And let's understand that this 1 over T2, so is actually composed of two contributions. What we call 1 over T2 tag plus 1 over T2 star. What is each one? Okay. The first one is what we call the homogeneous broadening, and the other one is the inhomogeneous broadening. So T2 tag, this one is the homogeneous, and this guy is the inhomogeneous. Now let's say something about those things. So here, I wrote that in many times T2 is much shorter than T1, but the time scale is dependent here, and we'll say something about that. So now here we come to understand, well, what is it? And here you have to understand that this coherence, it is not a single atom coherence. The coherence of a single atom behaves as we just said before. Assuming that you have a single atom sitting quietly, not interacting with anyone, then this coherence will live for as long as the excited state lives. But there will be situations, but we don't measure this. What we do measure is yeah, I'll take that away. So just to clarify, what we measure always is this. We measure the average over the ensemble of atoms and experiment of what? For example, if I'm talking about populations, then I'm looking at the average of C2 squared minus C1 squared. And this is basically going like, so this one is, yeah, as we said, it's decaying. And when we think about this, C2, C1 star, averaged over the ensemble, we'll see that this has some, well, what we called it, it's sigma T1 of time 0 times e to the minus T over T2. Why is it that it decays? Well, think about this. I can describe two possibilities. Let's think of the first one. One thing is, we just said, for example, that, look, if I take a short pi over 2 pulse, I'll end up in the UV plane. And then I'll just leave it. So it will evolve according to the detuning. If the detuning is 0, it will not move. If the detuning is non-zero, it will start moving around the plane. But what is the detuning? Is it well defined? The answer is maybe different atoms see different detunings. For example, if the atoms have different velocities, they have Doppler shifts relative to the laser. So for an atom that is sitting, maybe the detuning is 0. For an atom that is flying in one direction, the detuning may be positive and it will be running in this direction. For an atom that is flying in the other direction, the detuning is negative and it is rotating in the other way around. So what we see is that because of inhomogeneity of the velocity, some atoms are standing, some atoms are moving, and this is a thermal distribution, so we have all kinds of velocities. Some atoms are running forward in the UV plane. Some atoms are running backwards in the UV plane. Some atoms, and this entire thing, you have a distribution that very quickly covers the entire plane, and you're averaging out to 0. If you're looking at the average, so the fact that, just the fact that the ensemble is not homogeneous. You could have a different situation. For example, if we're doing something in a solid. In a solid, say you have a crystal, and you have not atoms, but impurities. I mean, if we don't want to talk about the entire crystal, because the entire crystal has bands you've learned about. We're not going to go into solid state. We want to talk about isolated atoms. How do you have isolated atoms in a crystal? Well, those are impurities that are sitting somewhere in that crystal. But still, this impurity sitting here and this impurity sitting there, they have a slightly different environment. Their environments are not exactly the same. They're not moving anywhere. But their environment slightly shifts their energy levels. So what is zero detuning for this impurity sitting here in the crystal is not zero detuning for this other impurity sitting there. This is inhomogeneity in space. The atoms, or for example, I'll give you another point. As you've already heard, there's a Stark shift. There's also a Zeeman shift, right? If I put a magnetic field inside, I'll shift the atomic levels a little bit. If the magnetic field is not homogeneous in space. So atoms sitting here feel one magnetic field. Atoms sitting there feel a different magnetic field. So the detuning for the atoms that are in this location is going to be different than it is for those here. And if I'm doing an average measurement over all the ensemble, then this inhomogeneous broadening of the energy levels, the detuning is, that's just it. The detuning is not the same at every location or for every velocity within the ensemble. And then that means that some atoms, so if I look at on the entire ensemble, some atoms see some positive detuning, so they're running like this. The others see negative detuning, they're running like that. And on average, very quickly, the distribution broadens across the UV plane, and on average, I see 0.
So you're talking about the second momentum shift, not the first momentum in the average.
What?
Second momentum in the average, like.
Yes, so I'm talking about the width of the distribution.
Yeah, the average will stay the same. Until
yeah, but the average.
It's spread the entire space, and then you can see
but what you see is that the average decays. Indeed, you know, what you see is that, okay, I put everything here. So the average stays indeed here. You know, the average behaves as you expect, but it also just shrinks. The average shrinks because of what? Because of those guys that are running faster and the others that are running slower, and very quickly they start to either cancel each other or cancel you.
If you measure second momentum in any operator.
So that means, for example, where will we see this? If I do a Ramsey experiment, meaning I go up, wait, go another up. This Ramsey experiment will be limited by T2.
But I mean, if I want to measure it.
What do you want to measure?
Let's say I measure the average. I will measure an average that is decaying, but it will
Yes.
stay in the same spot. But I can see.
Well, but very quickly you will not be able to see anything, but you know, because an exponential decay very quickly becomes 0.
It's easier to see a physical shift in the second momentum if I measure the second momentum. Because
Well, momentum is theta, and I think you mean moment.
Yeah.
But second moment of what?
The decay.
I'm not sure I follow you. You'll have to explain this.
Later.
Okay. So, so we understood what this guy is. So T2 is inhomogeneity. So T2 is due to inhomogeneity. Homogeneity, I'm not sure. Between atoms. It can be different velocities or positions that cause different delta, different detunings. And this is a clear source for decoherence. Now, but now let's suppose that I take a perfectly homogeneous ensemble. What will happen then? Or I'll show you in a moment. What is a point of importance here is that, look, this is a problem, but it's not a problem for every atom. I mean, each atom has its own very long lifetime. The problem is the fact that don't all atoms agree. And then there's the homogeneous part, which is what happens to every atom. So that was T2 star. And if I want to say something about T2 tag, I think though, okay, we'll soon take a break after completing this. So we were saying something about T2 tag. This is the homogeneous decoherence or homogeneous broadening. What is this? This has to do with how long does a single atom within the ensemble remember its phase. So if I just this atom, does it have a well-defined phase? The problem for now was that all atoms had a perfect well-defined phase. It was just not pointing in the same direction. So the average decayed. Now, so this was in homogeneity between atoms, and this is homogeneous. This is what we can call the single atom memory. You can even say phase memory. Now, of course, this is limited by spontaneous lifetime. So what are the sources of this? This would be spontaneous decay is the ultimate limit for this. So the same one that we had before, but also collisions, which in other terms is called, so these are the sources. And here, those were the sources, never mind. Collisions, or in other words, this is called pressure broadening. Why do we consider collisions? You could say, well, what are we talking about? Collision is something that happens to this atom, but not to that one. Yes, but this is something that has to do with me. Every atom collides eventually. And assuming that my measurement time is sufficiently long, then every atom within that measurement time will have an average time of collisions. Now, if my measurement time is extremely short, then indeed this would be very well below 1, and most atoms will not have collided, and only some of them would have. But if I wait long enough, and this is usually the case, I don't know, that the collision time is something like a few nanoseconds, and my measurement time is a few microseconds, maybe. Then all atoms will have collided during that time. And on average, about the same. Now, why is a collision important? And the point here is elastic collisions. So if we discussed collisions before, the collisions that affect the population decay are inelastic collisions. Collisions that change the state of the atom, that either take out energy or put energy into the atoms. Whereas the collisions that affect the phase decoherence are elastic collisions. Why? Elastic collisions do not change the energy state of the atom, meaning they don't move atoms from the ground to the excited or the other way around. So the populations remain the same. But when those two atoms come together, they feel each other. What happens? They have an interaction term, just like a field. I mean, there is an atom here, and there is a charge distribution getting close to it. When they're far apart, then they don't feel anything, because this is on average neutral, and this one's on average neutral, so they don't interact. But when they're close enough, then the electron can feel the fact that here the nucleus and the electrons are not sitting at the same place. And there will be a dipole-dipole interaction. For example, this is a dipole that is oscillating, and this is a dipole, and they come close and they feel each other. And this dipole-dipole interaction will come into the Hamiltonian. And what will it do? It will change the energy levels. Where was it? We had a Hamiltonian. This Hamiltonian that we had before, that said we have 0 delta E, well, not E, it was omega, it doesn't matter. This Hamiltonian is assuming that we know everything, that the interaction is only, it's a bare atom with, and also a field. But there are other terms. I mean, when two atoms collide, then this Hamiltonian is changing. What does it change? It means that for a while, these levels, the ground and excited, they are shifted somewhat. They get shifted slightly and go back. Now, if I look from outside, I don't see that anything happened, but there's something did happen, because that means that the rate of acquisition of phase has changed. We assume that they acquire a phase at a rate delta relative to the laser. But if they collide, then there was a while during the collisions, their energies were shifted. So the rate of phase acquisition has been changed. So they come into a collision and they come out, and almost nothing changed except a random phase. They acquired a random phase that we have no control over. So that means that a single atom, by a collision, now tell me, now we need to discuss about the nature of the collision. Is it a hard collision where a single collision completely loses memory? Or is it a soft collision where it only loses a little bit of its phase, but it becomes like some kind of a random walk? With every collision, it loses just a bit of the memory, and only after, I don't know, 10 or 100 collisions, it will completely have lost any memory of its original phase. But that doesn't matter. The fact is that a collision induces a random phase that we don't know. That means that basically an atom that was sitting nicely here on resonance will come into a collision and move somewhere and stay there, because it's still on resonance. But the phase is unknown. So these are sources for, so these are sources for broadening, and okay. So I think let's take a break now. And after the break, maybe I'll say probably, no, I won't say anything more about, I think we'll stop here about the two-level system and start saying a few things about a three-level system, but we won't say anything about a four-level system. But there are very beautiful things that we can see about the three-level system. And this, after the break, which will take from now and for the next 12 minutes. So at 11:45, we'll continue. Quarter to 12. And we'll continue probably until around 12:30, maybe a little bit later, because we started a little bit later. That's it. Okay, 10 minutes break. 12 minutes break.
לא, כי זה כאילו נגמר על לימודים
היי הו. מה שלומך, דוקטור?
למדת.
לימדתי.
לא, למדת, אמרתי לך להוריד את המסכה, למדת.
כן, כן, ולימדתי. אבל עכשיו כולם שומעים אותך, אז זה משודר ביוטיוב לייב. תיזהר. מה שכן, אני מחפש כוס. יש פה? כוסות סתם? נפלא.
תגידו לאבי שהוא יושב את המיקרופון פתוח, אז שלא יגיד דברים פליליים.
הוא יצא מהחדר מזמן, אין לך מה להגיד לו.
אז תגידו לו, לא יודע, הוא בטלפון.
באו להגיד לך שאתה עדיין המיקרופון.
כן, כן, אני יודע, אני אפילו עושה מזה קצת צחוק. אבל לא, זה לא היה, לא לדאוג, זה לא היה זה. אין לי כוח להוריד את המיקרופון בהפסקה. Any questions?
אבי,
Yes.
אתה יודע, עד שבי נשתיים סטאר, אנחנו מניחים תלות באחד חלקי, או אנחנו סתם ביטוי כללי ויש לנו, כי נגיד, בקורס אחר למדתי שהטיונינג הוא כמו לורנציאן, סביב מרכז כזה, וכל השאר, כאילו, מתמצא כמו לורנציאן, אז כאילו, זה לא בדיוק אחד חלקי, נשתיים, זה קצת יותר מסודר.
לא, למה? רק רגע. לא, זה לא נכון. כלומר, ההתייחסות של ה-Decay, אני לא אמרתי איך או נתקן את זה. אני טוען שלא משנה מה ה-distribution של מצבי הדיטיונינג האפשריים, בסופו של דבר האפקט יהיה אותו אפקט. כלומר, מעצם העובדה שיש distribution של במקרה שלנו detunings, לא אכפת לי אם הדיסטריביושן הזה הוא לורנציאני או גאוסיאני, האמת היא שהוא יכול להיות כזה או כזה. האפקט הסופי מבחינת מה שקורה ב-2-level system זה אותו דבר, זה אובדן של קוהרנס. אז אני לא בטוח מי שאל, אז אני גם לא בטוח לאן אני מדבר, אבל...
מלמעלה.
מה זה? כן.
יש את כל מלמעלה ששואל שאלה.
הכל... אז זה ענה על השאלה?
כן, אני ודאי לי שזה דורך, השאלה היא כאילו אם זה 1 חלקי T2 וכאילו זה היחס הנכון, סתם או שזה לא כזה דחוף לנו יחס נכון.
תראה, קודם כל יש דעיכה. אז ברגע שאתה שם 1 חלקי T2, כמו שאמרנו זה פנומנולוגי. אז נכון שעקרונית אולי בזמנים מאוד קצרים, הדעיכה היא לא בדיוק אקספוננציאלית. ויכול להיות שבאמת בזמנים מאוד קצרים זה מתחיל איכשהו אחרת. אבל ברור שאחרי זמן סביר זה פשוט יהפוך להיות אקספוננט דועך. כאילו מה שאני טוען זה שהאקספוננט הדועך תופס את ה-leading order behavior של הדעיכה. ובינתיים הפרטים לא כל כך קריטיים.
סבבה.
אוקיי. פלופ. טוב. is it time? לא, יש עוד 6 דקות. מלא זמן. תיאבון. אתם צריכים להזכיר לי שמות. היתרון הגדול של ללמד בזום זה שאני רואה את השמות של האנשים, אז אני זוכר אותם. וחוץ מזה יש מלא חסרונות. אבל... כן, יתרון אחד לזום יש, זה עכשיו. ואני זוועתי, אני לא זוכר. כן, יאללה, מדבקות. מה? תראה, אז זה בעיה, כי הם לא טורחים להדליק מצלמות. אז אני רואה שמות ולא רואה פרצופים. לעומת זאת פה, פרצופים. נו, שמות. אני אדביק אתכם לשם. מסביב יהום הסער. נכון, אבל אני זוועתי בשמות, אני שוכח גם מהר. ה-Coherence Time שלי הוא קצר מאוד. מתניה. אני אשתדל לזכור. אבל... טוב. אאוץ'. Okay. Poof. Tov. We continue. Actually, so yeah, we're back. And the plan now is to say something about okay, there is one are we all here? Yes. And okay. So I want to start saying something about higher situation. As you know, in physics, we count one, too many. Or in case of levels, then one level is completely a non-interesting case. So we count 2, 3, many. So we're going to say a few things about the three-level system. There are some beautiful things that can be said about this. So, okay, we can start from. So we want to talk about three-level systems. Now, with 3 levels, the problem is that you lose this convenient, intuitive picture of a fictitious vector. Because there's no longer just one spin. I mean, maybe you can think of 2 spins, maybe like 2 coupled pendula or 2 coupled spins that one goes and the other, but it becomes, the dynamics become too complicated. It's not, there is no more a Bloch, a nice Bloch picture of it. But still there are beautiful effects. So, and the effects are important. For example, so there's the main thing that happens is that the atomic coherence can do suddenly much more than it could for the 2-level system. And you'll see effects Okay, we'll talk a little bit about effects like stir-up. Stimulated Raman adiabatic passage. It's the adiabatic passage that you saw before on steroids. Really, like, you know, population goes from the first state into the third state through the second state, but without ever being there. So that, you know, sounds great, right? So, I have the initial state, and it is coupled by a laser to some intermediate state. And then this intermediate state is coupled by another laser to a final state. And I can have a situation where I have transition, I have those two lasers on, I'll transfer population from the initial state into the final state, but if I look, does it ever visit the excited state on the intermediate state? The answer is never. So how do I make a transition through an intermediate state without ever being there? And that has to do with some adiabatic passage. So this is, yeah, stimulated Raman adiabatic passage. Or they're all related, of course. EIT, electromagnetically induced transparency. Electromagnetically induced transparency. What does it mean? It means that I have a medium. I shine one laser, and suddenly this medium becomes completely transparent to another laser. And it becomes extremely, like an extremely narrow line. They're interesting effects, they're really beautiful effects, and we'll discuss them shortly. There's also tricks of lasing without population inversion, meaning a situation where you could have a laser that has gain, so it produces stimulated gain, but without any population inversion. In standard laser physics, it cannot happen. In order to have gain, you need to have more population in the excited state than in the ground state, in the lasing transition. So all of those things can happen in a three-level system, and they're due to the atomic coherence. Now let's define the system first. So there are going to be three levels. And of course I can have what we would call, then you could say I can have a ladder system. So then we would have state 1 and state 2 and state 3. Yes?
It's hard to see what you're writing in the left side because the camera. I can't see it.
I can see the entire board. So maybe it has to do with the aspect ratio of your screen or something? Because
okay.
Maybe.
I will try to fix it.
But but in any case, I'll move a little bit further into the. See if you can fix it, great, and if not, but you'll understand in a moment. I mean, all I said was a ladder, and there are three levels in there, just standing like a ladder. Now and then, but this is just an orientation. What you will have is then you'll have one laser with some detuning, so there will be some omega 1, 2, with some detuning delta 1, and then another laser that takes you from here with another detuning. Now, there could be a lambda system. What does it mean? There are two states, two low states, and one excited state. Well, and then again, there will be a laser 1, so this would be state 1, this would be state 3, this is state 2. And we could have here a detuning and then another laser with another detuning. So this one would be like omega 1 and omega 2. Of course, you could have also a V system, V-shaped system. I think that concludes all the possibilities. But you'll see in a moment that they're really all the same, at least as long as we don't consider decay. And right now, we're not going to forget about decay. We're not going to say anything about spontaneous decay so we're going to analyze this assuming perfect behavior. And under these assumptions, then if I call this one 1, 2, and 3, you can see that it's really just the same. So there's a laser here, detuning 1, and then there's a laser there with detuning 2, omega 2. No. Let's call this one 2 and 3. So they're all possibilities of three-level systems. We're going to focus on this one, which is the lambda system. But I'll show you very quickly why it just doesn't matter. So, but let's think about this. I want to ask myself, how does the Hamiltonian, so I have three levels. So we're going to assume that this is the case. I'll draw it just once and maybe with a big. So here, there's a state. So this is state 1, this is state 3, this is state 2, and we say that we need a different marker. Oh, it's a new era. And we just said, look, there is. So now you can see that there's going to be two detunings involved. And I'm drawing them on purpose in a convenient way. Meaning, I'll take laser 1, which has frequency omega 1. It is close to the transition from state 1 to state 2. And it has some detuning from it. Delta 1. And then I measure, I could say also there's another laser that couples state 2 to 3. And this laser has a different detuning. Well, it could be any detuning. Of course, I could draw something like this, right? And then have detuning delta 2. I don't do that. I do it in a way as if they continue one on top of the other. Meaning that I put here another laser that I put it here, and I draw the detuning delta 2 here. Of course, it doesn't matter. It doesn't matter where the arrow holds. And that means that the detuning of laser 1 on the transition 1 to 2 is just delta 1. And the detuning of laser 2 on the transition 2 to 3 is delta 1 plus delta 2. And of course, maybe delta 2 is, I don't know, negative delta 1. I mean, it could be, we still can have, and I can talk about the, and now we can say, okay, so what is the Hamiltonian of what's the bare Hamiltonian here? Okay, Hamiltonian of matter. How does it look? Well, we know how it looks. Well, this is a diagonal matrix with energy 1, energy 2, energy 3, and 0 everywhere. And of course, and it makes sense to call the first energy, let's call this one 0. Okay, the energy of state 1, let's reference that to 0. And if I ask myself, or generally the state, of course, is what? It is C1 times state 1 plus C2 times state 2 plus C3 times 3. Now, what about, okay. So, of course, we're going to do a rotating wave approximation pretty soon. I'll explain that in a moment. But if we think about what is the light-matter interaction, how does the interaction Hamiltonian look like? Then the answer is, okay, I have a laser. So let's, before we write it as a matrix, let's write it as a so let's write it as a something. So this is the interaction Hamiltonian is D12 times E12. Well, of course, you know, I'm going to divide by h bar because I'm going to take this to be a Rabi rate. But so yeah, I'll write it divided by h bar because for me I'm going to take h bar to be 1 very soon. And this is a function of time. So this E12 has an amplitude and excuse me, cosine omega 1t. And then there is this other one. So you know what, let's do it like this. We'll have 1 over h bar outside. And this is the interaction Hamiltonian. And there's another one, of course, which is D23 times E23 cosine omega 2t. Now, as we said, this is just a classical wave. Where is the operator? This is the operator. And this operator, what does it do? The dipole couples level 1 and level 2. You could think also of another field that couples level 1 to level 3. But in many cases, let's just, on one hand, let's say first, let's make the system as simple as we can. It's already complicated enough. And the other thing is that you'll see that the interesting effects are already here. And in many cases, this is indeed the situation. That you have, why is that? Usually, if this is an allowed transition, if the transition from 1 to 2 is allowed in one photon, and the transition from 2 to 3 is allowed, as due to symmetry, in most cases, the transition from 1 to 3 is forbidden. So the dipole, in many systems, the situation is that this dipole has a large dipole value, and the dipole from 1 to 3 is usually either extremely small or completely zero. So that's why, for both convenience and reality reasons, we choose to look at only 2 lasers and not involve a third. What does it mean? It means that this element couples. So here we have zeros on the diagonal. And here we'll have, I'll call this term. OK, in a moment, we'll do something. So here there's going to be D1. I'll just call it D1. E1 of T. And here the same. And here there's going to be 0 because there's no coupling from state 1 to state 3. And here there will be D2, E2. Now this is, of course, before we do any rotating wave approximation. But the rotating wave approximation works here just as it did before. So I'm going to do something on the board that on your paper is less convenient, but if you have a tablet, then maybe you can do the same. So now I'm going to say, let's go to a rotating frame. What does it mean? It means let's rotate those states according to according to something. Okay.
Avi?
Yes.
Why we didn't have interaction between the first level and the third level?
That's what I just said. That usually this transition is forbidden. I'll say why. If you remember, I don't know if you remember, but maybe at some point you learned that the allowed transitions in the interaction are only transitions that involve a single unit of change in angular momentum. The light can take you from state of angular momentum 0 to a state of angular momentum 1. So delta angular momentum is unity. Now, that means that if the difference in angular momentum from here to here is 1, and from here to here is 1, then the difference in angular momentum from here to here is either 0 or 2. And that would mean that this transition is usually not allowed. Now, conceptually, you can include that as well. There's nothing to stop us from doing that. So, but it makes things even more complicated. So let's keep it as it is. So now we want to rotate. So suppose now that I'm rotating. So what we're going to do is now we're going to go to a rotating wave, rotating frame. Now, as you know, to move to a rotating frame only means that we decide that we acquire a phase at a different rate. So I can say, okay, this state is indeed C1 times 1. And then C2, I'll give it a phase. Which phase? There's a detuning here. So I'll write it just like this minus I omega 1 t. It's 2. And then plus C3 times what? Times e to the I. And then let's see. Laser 1 goes up and laser 2 goes down. I mean, what has to be here is this. Omega 1 minus omega 2 t times 3. Yep. Do you understand why I chose this? Now, of course, so when we do this and just consider the total, okay, so I'll just say how it's done, but I'm not going to do it. I urge you at home to do what I'm doing quickly in a detailed manner. But what's the time? Yeah, okay. So, yes. We're going to, so when I do that, eventually I'll have to write psi dot equals H matter plus H interaction times psi, which in other words will mean that we will have here C1 dot C2 dot plus, or minus, sorry, minus I omega 1 C2 all times e to the minus I omega 1 t. And then here we'll have C3 dot minus I omega 1 minus omega 2 C3, and this entire 3 times e to the I. I'll write here delta omega just so that I don't get things to be too long. And even here we'll write delta omega C2, and this is, as we said, omega 1 minus omega 2. And this equals what? This times C1, C2, e to the I omega 1 t, C3, e to the minus I delta omega t. And here we have, as we know, 0, epsilon 1, or how did we call them? Yeah, epsilon 2, epsilon 3, and this d1. So let's just call it, no, not yet, d1 e1 of t, d2 e2. This is still time dependent without any approximation. So far, nothing, there is no approximation. But you can clearly see what will happen. Here we will have omega 1 plus omega 1. And here we will have epsilon 2. Now omega 1 and epsilon 2 are shifted by delta 1. That is the energy separation. So this is epsilon 2 is the energy difference from 1 to 2. And omega 1 is nearly that. So when we do a rotating, and the same will happen down here, epsilon 2 is almost delta omega. What is the difference from it? It's delta 2. So what I'll end up in the end, so now I can do a rotating wave approximation. How? Then we'll remember that this d dot E contains both positive and negative frequencies. And then we will have terms that rotate at e to the minus I omega 1 and therefore are stationary. Those that are rotating together. So within this frame, when I throw out, cancel out e to the I omega 1 from the second row, and those terms will be stationary. And the other terms that are counter-propagating, those that are rotating at here, we would have e to the plus I omega 1, and here there's going to be e to the minus I, so they are counter-rotating at twice the frequency, and they are thrown away because they are not interesting. So when we do this, expand, throw the counter-rotating terms. So when we do that, then we go to the after rotating wave approximation, and this is rotating wave approximation twice, both for the for each of those levels, but it's exactly the same thing. We get the rotating wave approximation Hamiltonian, which looks like this: 0, delta 1, delta 2, and then here omega 1 star, omega 2 star. That's convenient, or at least, yeah, well, in a sense it makes sense. And what does this tell us? This tells us that this vector C1, C2, C3 from the rotating wave frame dot equals this Hamiltonian rotating wave approximation from here, so I won't write it again, times C1, C2, C3. If you want to be exact, there's an I here, and maybe there's a minus sign, and I never remember. Okay, so this is just formality of how we act and look on a three-level system in the same concept as we did for the two-level system. But now, let's start asking ourselves what interesting thing can happen. Yeah. Now, I have a little bit of a problem. So, okay, so now let's solve this. But let's solve this only in one way. We're not going to be do many ways. We're only going to do the dressed atom picture. So what we're going to say is, I want to diagonalize this. Okay? It's a 3 by 3 matrix. It's not very hard to diagonalize. I want to find what are the eigenstates of this Hamiltonian, the Hamiltonian that includes the field in it. So we're going to do a dressed atom analysis. We're going to diagonalize this, and we're going to make one convenient assumption, and that is that delta 2 equals 0. Okay? And what does it mean to assume delta 2 equals 0? It means that what we have is exact two-photon resonance. Delta 2 is the detuning, the total detuning from 1 to 3. You understand what I mean? You can be detuned here with a delta, but the same delta is there. So if omega 1 minus omega 2 is exactly the energy difference between those two states, then that means that we are what we call on exact two-photon resonance. So we're going to do dressed atom analysis, and we're going to look specifically in the case of for delta 2 equals 0, which means on what we call the two-photon resonance. Now, honestly, I use this term, two-photon, one-photon resonance, because this is the standard term. But there's nothing photonic here. This field is classical. It doesn't relate to photons in no way. We talk about one-photon absorption, two-photon absorption. All of those things are very nice. But they're completely classical. You don't need to say the word photon in order to see them. So far, there's nothing photonic here. These are just numbers. There's nothing special in the field. It's just a classical number. So these terms, don't let them fool you. Now, on two-photon resonance, where delta 2 equals 0, so we have a Hamiltonian that looks like the rotating wave Hamiltonian. It looks like 0, delta 0. There's only one delta now. Omega 1 star, omega 2 star. Maybe, wait, there is something that maybe I'm wrong about. I think that I should flip the stars here, because usually we associate the star with the down transition and the field with the up transition. So let's see. The transition from 1 to 2 doesn't have a star, and this one has. And then the transition from, this is the transition from 2 to 3. This should be starred, and this one should not. And I'm sorry, let's do the same here. But this is just a convention, of course, because, you know.
It's just a name, it doesn't matter.
Yes. So if I want to, so now I want to calculate the determinant of what? Minus lambda, delta minus lambda, omega 1 star, omega 2 star, omega 2. What is this determinant? Well, you know, this is, well, minus lambda times delta minus lambda times lambda, so it's plus lambda squared. Minus lambda times omega 2 absolute value squared. This, what?
So it's a plus lambda. You get a minus in the direction now.
Correct. Thank you. Some people remember. And then what do we have? The next one is, I don't know, minus omega 1 times omega 1 star omega 2 minus lambda, and that's about it.
No,
What?
just minus lambda.
What did I do wrong?
You just wrote it very
Ah, of course, of course, of course. So omega 1
So it's
plus omega 1 lambda.
Absolute value squared.
Why is omega 1 absolute value squared?
Because you do omega 1.
Omega 1 times omega 1 star, of course. That's what it should be. So we have here plus lambda times omega 1 star, absolute value squared. Very good. And this we want to be equal to 0. Convenient. So there is, so what do we get? We get here lambda. And that's it? Yeah, the last one is 0, so never mind. So we have lambda times, here we have lambda squared minus delta lambda plus, no, not delta lambda, just delta. Yeah, delta lambda. What did I do? No, wrong.
That's fine.
No, there shouldn't be Venus squared. Lambda is out. Here there was going to be lambda times delta minus lambda squared plus omega 1 absolute value squared plus omega 2 absolute value squared. Well, at least, and now the point is one of the eigenvalues is 0. That is going to turn out important. We have an eigenvalue that no matter what, doesn't matter what the field intensities are, doesn't matter what the detunings are. And there is an eigenstate that has an eigenvalue 0 always. So what we have, so first of all we have lambda 0 equals 0. That's the first eigenstate. And then there's going to be two other eigenstates here. So there's going to be what we call lambda plus minus, two eigenvectors. And they are what? So let's see. Minus delta over 2 plus minus, oh, sorry, not minus delta, just delta over 2 plus minus square root of delta squared, right, minus plus or minus? Plus, well, plus, fine. Plus omega 1 squared plus omega 2 squared. And all of this divided by 2.
נראה לי אם זה פלוס בשורש אז צריך להיות מינוס כי השאלה אם הוצאת מינוס החוצה או לא.
Honestly, I don't care.
אחד סותר את השני?
No, they don't. They're fine. I think it should be a plus, but there is the right solution, and we both agree what it should be. And no, what I mean is that it doesn't matter. Why? Because there are going to be two eigenvalues here. Now look, there's this eigenvalue, and there is okay, I'm sure that you can solve what should be right here. And remember, we were doing things too quickly. So here we should have minus 4ac. Now c is positive and a is negative. So there should be a plus. The plus here is right.
Shouldn't there be a 4? Yeah, there should be a 4.
There should be a 4. You're right. So there should be a 4. So let's do something else.
You can put divided by 4.
Yes, let's take the 2 outside and forget about this guy. So I'll do this way. Delta squared divided by 4. And the 4 factor went out, And here we'll have plus omega 1 squared plus omega 2 squared. And what about the factor 4? It went out, became a 2, and got lost with the division by 2. Okay. Now they go with eigenvectors. The only one that I want to find is the one that goes with the eigenvector 0. Because, look, now what I want to show you is that first there is one state that has an eigenvalue 0 independent of whatever fields we put in. And there are other two states, two eigenstates, that have an eigenvalue that does depend on the field and on the detuning. Now, what is this vector V0? What is it? So,
state is negative to the first state.
What?
C1 equals negative C3.
Yes. So indeed, there's, and we can put here. So I'll write it like that. It is omega 1 or omega 2? No, this is omega 2. I think also star, and here omega 1, and here 0. And there is normalization. Why did I do it like that? Minus, I think, here. What? Which one should be a star? This one should be a star?
Yeah.
And this one?
Also.
Both of them should be.
Yeah.
Good. Okay, so be it. Now, and you can see that indeed it works. So you can see that this state, and we can write also those guys, those V plus minus, but honestly, they're less interesting. You can find them. I'll write them for you. They have something like, they have, I'll put, what I want to say is that those guys, I'm not going to say much about, they have a normalization factor here. And they have 3 components. They're important, but because we are at the end of the meeting and we want to say something interesting, then the main thing that is different is that those guys, they do involve the intermediate state, and this one does not. This one involves only the first and the last state, but doesn't involve the intermediate state at all. These two guys, they do. They involve the intermediate state. They have something here, and they have something here. But, and specifically, they have the excited state written inside strongly. So now, in the last few minutes, let's show you stirrup. Because now you can. So what is this? We call this state with the 0 eigenvalue the dark state. It's not the dark lord. It's just the dark state. First of all, let's see that it makes some interesting sense. For one, let's assume that, oh, I just erased yeah. Let's draw it again. So there's 1, 3, 2, and then there is laser 1 with omega 1 and detuning delta. And here there is laser 2 that, as we said, because delta equals 0, then delta 2 equals 0, I wouldn't even write it. So here there's omega 2. And I can even put it like that. Now let's assume that laser 2 is off, which means that omega 2 is nothing, 0. Not omega 2 small 1, omega 2 big 1. So this one is 0. So what is the dark state? It's state number 3. Okay? So let's just remember that if omega 2 equals 0, meaning laser 2 is off, then this V0 is just state 0, 0, 1, or it's just state number 3. Now, if omega 1 is 0, or meaning, of course, laser 1 is off, then this state V0 is state number 1. And it makes sense. So that you understand why we call it the dark state.
Nothing moves.
Yeah, this is the state that is decoupled from the light. If the laser 1 is off, then of course state 1 just doesn't see anything, doesn't move anything. It's dark. The light doesn't. But the point is that those two are extreme cases of something that is more general. There is a dark state always, even when the two fields are on. So now, or in other words, let's say the following. I'll move adiabatically from having laser 1 off and laser 2 very strong to the situation where laser 1 is very strong and laser 2 is completely off. And then what will happen? I will be in an eigenstate. In the beginning, why will I be in an eigenstate? Suppose now that all population is in state number 1. Okay? All population is here. I turn on that laser. It doesn't do anything. Population is still there. Now what I do is I slowly reduce the intensity of this laser and increase the intensity of that laser. Okay? Something happens in between, but I do this very slowly. So what is it? I started in the eigenstate V0, which was identified with state 1. I slowly change, and I will stick with this eigenstate. This is what adiabatic following is. With adiabatic following, you follow the state that is at your energy. And what do you end up in? You end up in a situation where laser 1 is very strong and laser 2 is off, and then V0 is state 3. So we transformed state 1 into state 3. We completely shifted all the population from state 1 to state 3. Was it ever in state 2? The answer is no. State 2 is never populated. Magic. So So we can do so we're talking about stirrup. This is what we just saw. So we start, so I'll do some kind of a diagram. I start from, this is the course of time. And in this course of time, I'll start this is the intensity of laser 1. Sorry, not laser 1. This is the intensity of laser 2. This is the intensity of laser 2. So this is what we would call omega 2. Absolute value squared. But let's even write it like this. And this, never mind. And this is the intensity of laser 1. And then we can ask ourselves, okay, so here, in this part, the zero field, this V0 is state 1. In this part, V0 is state 3. In between, there's a superposition, coherent superposition of 1 and 3. So here, in between, there's a flow of, so here, if I look, there's some alpha 1 plus beta 3. And those alpha and beta are slowly changing. And you continuously transfer from being at 1, alpha is slowly going down, beta is slowly going up, and you end up completely in state 3, and you've never visited state 2. So, now everything that is interesting about the three-level system comes from the existence of this dark state. Now, let's see what will happen if we are not exactly on two-photon resonance. If you're not exactly on two-photon resonance, then this dark state is not exactly dark, and it will have some contamination of the excited state. That's one thing. But two-photon resonance is not very hard to get. I mean, to make sure that the difference between those two lasers is exactly this energy difference is not necessarily very hard. Then, okay. We'll talk a little bit more about more details of the three-level system here. So if there was one thing that I did want to do here, and that is to draw. So I can say now, yes. So if I ask myself what happens to the populations, so the population of state 1 starts high. This is P1, the population of state 1. It starts high and decays. And the population of state 3 starts low and increases. And this P1 is just C1 absolute value squared. And I'm sorry, there's too many elements on this board. Things become too dense. But, okay. So, what we learned. Oh, there's one thing that I want to say about the magic of it. Is it really magic? The answer is, well, not really. It's beautiful. What it means is that you can make there is a superposition of those two states where what? How is it that the excited state is not involved? Because the excited state can accept amplitude either from state 3 or from state 1. And those two would interfere. If you align the phases of whatever you can excite from state 1 to be exactly opposite to the phase of whatever you can excite from state 3, then they would cancel. So the fact that you can have a situation where there is no population in state 2 makes sense in terms of destructive interference. You have destructive interference of the contribution from the transfer from state 1 up to and the transfer from state 3 up. Now, is it indeed possible that nothing will ever be in state 2? The answer is yes, almost. And you can think about it in the following way. Suppose that I have, I have water in bucket 1, and there's a pipe going from bucket 1 to bucket 2. And then there's a pipe going from bucket 2 to bucket 3. Can we have water always in bucket 1 and bucket 3 and nothing in bucket 2? The answer is yes, if the transfer is very quick. If every drop that goes from bucket 1 to bucket 2 immediately is transferred to bucket 3, then bucket 2 remains always empty. Or whatever stays there is very, very little. And if you think about it, this is basically what we're doing. We start with omega 2 very strong. What does it mean? Whatever comes up to state 2 is immediately taken down because this field is strong at the beginning. So you start raising things very slowly and taking them down very rapidly. So there's nothing left in state number 2. And in the end, what do we do? Well, in the end, this one gets rather filled. So you don't want to drive it strongly because then you would be starting driving things back up. And then what happens is you increase the driving here. So you are, as this state depletes, you have a more intense driving to take this population up. And then you reduce this one slowly. And eventually what happens is that, yeah, population does go through state 2, but only very little. At any point in time, there's very little. So if I look at state 2, I almost always see practically nothing. So what we do see is if I look at the population of state 2, I would see it somewhere here. It would be very, very low. It wouldn't be completely zero. Okay, I think now is a very good time to stop. So let's stop. Now this dark state, this destructive interference that eliminates the one state out of the dynamics is very interesting. You just saw that it can allow you to have an adiabatic passage from one state to another without visiting the excited state completely. It's very useful because the excited place state is lossy. But those two ground states, they're probably not. And this has to do with electromagnetically induced transparency. We'll mention that next week. And then we'll leave the matter. That's it. Done with quantum matter and classical light. And now, only classical light. We're going to discuss classical coherence. What does it mean to be coherent or incoherent in both space and frequency in terms of classical light? And what is the classical photo detection statistics? That is important. Because you need to know classical physics before you start to discuss quantum physics. Okay. See you next Tuesday. As usual, here. Any questions from home? Or questions